Hi everyone and welcome back to the channel. Today we are going to take a look at quadratic functions as an extension to what we learned in the chapter of quadratic equations. As a brief overview, in this chapter you'll learn about the key characteristics of quadratic equations, for example their shape, intersects with the x and y axis, axis of symmetry, maximum and minimum points, and how to identify them. The second is how to sketch any quadratic equation, and the third is on quadratic inequalities, which is when is the function above or below a certain number. But before we go into any of that, what is the difference between what we learned in Chapter 2, Quadratic Equations, compared to Chapter 3, Quadratic Functions? Long story short, is that Chapter 2, we learned how to find solutions, and these are intersects with axes, with lines, etc. In Chapter 3, we'll learn to describe the entire function. Difference is, in Chapter 2, what we do will be one-off to find a solution or to find one answer, and pretty specific to the problem. In Chapter 3, we'll know all there is to know about a certain function. For example, in Chapter 2, I can ask you to find the value of x that causes the equation 2x squared plus 4x plus 2 to equal to 0. And you'll be able to find it. This is called finding the solutions or intersects. Essentially, it says this equals to this, and here the solution is x equals to -1. In Chapter 3, what we'll be doing is a little bit broader, because it will be about the quadratic function itself. Remember that the function represents a set of rules that relate our inputs x to our outputs y. Essentially, this tells us that for every input x, we do something to it to get the output y. So for the function fx equals to 2x squared plus 4x plus 2, once we understand how it works, we will know all there is to know about it. For example, its shape, when it gets flatter or steeper, when it turns, what is its maximum point, etc. etc. Following on from our earlier example of the equation y equals to 2x squared plus 4x plus 2, let's go through a few of these properties. Number 1, this equation forms the shape of a curve. So you can see it's a U shape over here, and no matter how far I zoom out, so you can see the increments on the x-axis are getting bigger and bigger, 20 to 50 to 100. It always stays this curve shape. Second thing to note is that the curve, as it increases faster than if it were to be a straight line. So it curves upwards. So to give you an example, check out what happens if I add the line y equals to 4x plus 2 over here on the graph. And I chose y equals to 4x plus 2 because that represents the bx plus c portion of the equation that we have. So you can see that the curve is above the straight line at all points, which indicates that our quadratic function is bigger than the linear function. So for example, when x equals to 2.15, y equals to 19.845 on the quadratic curve, but on the straight line at 2.15, y is only 10.6. The third thing is that this curve forms a U shape with only one turning point. So no matter how far out you zoom, the curve only changes its direction once over here. It doesn't say U-turn up here to come back down to 0 again. No, it only turns one time. And if our coefficient of x squared, a, is positive, then the curve forms a smiley face, positive for smiley, and it's a minimum function. If a is negative, it's a maximum function because it's a sad face, negative for sad face. Next, the curve is a symmetrical U shape. It's exactly symmetrical about the turning point over here, in fact. So let me just move the curve a little bit, changing our b to 0, and you can see that it's actually a mirror image of itself upon the y-axis. So for example, when x equals to negative 2.01, y is 10.08, and when it's positive 2.01, y is also 10.08. It's a mirror image of itself. The quadratic function always intersects the y-axis at some point. So for example here, the intersect is at y equals to 2. If I put in any other random function, so if I say a is 8.2, b is negative 67, c is negative 27, it still intersects the y-axis if I zoom out a little bit when x equals to 0. At y equals to negative 27, it always intersects the y-axis. But for the x-axis, it only sometimes intersects. And this is when the discriminant, b squared minus 4ac, is more than or equal to 0, as we learned in the last chapter. Last thing I wanted you guys to see is just what happens when you change the values of a, b, and c. So for a, as I increase a, the graph actually gets steeper and steeper. So it increases faster and faster because the coefficient for the x squared term is larger. As I decrease it, it gets broader and broader, and when it reaches 0, it becomes a straight line, because then it's no longer a quadratic equation. And when it goes negative, it inverts on itself. So negative is sad face, so it becomes a maximum curve, and the more negative it gets, the steeper it gets. For b, it's a little bit more tricky. You don't really need to know this, but this is just for your information. As I increase b, what happens is I'm actually stretching the curve to the left. And as I decrease b, I'm stretching it to the right. So it gets, broader and further down. It gets broader as I make b larger. And lastly for c, c is a constant. So it's pretty simple. As I change c, it just moves the curve up and down. It's just a pure translation. Up, down. Now let's go through a real-world example for your knowledge. And the example I'm choosing here is from the NBA, and it was when Steph Curry drained the buzzer-beater three-pointer against the Oklahoma City Thunder. Here is the clip I'm talking about.
They do have a timeout. Decide not to use it. Curry, way downtown. Bang! Bang! Oh, what a shot from Curry! With 0.6 of a second remaining.
In my opinion, one of the shots that cements Steph Curry as one of the greatest three-point shooters of all time, but I digress. So looking at this picture here, when we see a curve, we should think quadratic. So let's see whether we can learn anything about this shot using the knowledge that we have. For example, we can ask, how long was the ball in the air before it entered the basket? So I'll just put this into a two-dimensional image for us to see this clearer. You'll see Steph, see the hoop, and you'll see the shot follows a curve which resembles a quadratic function. I give you a little bit more details, such as the release height of 1.9 meters above the ground, that's his height. The basket is 10 feet off the ground, that's 3.05 meters. Steph is 9.6 meters away from the basket when he makes this shot. And lastly, how fast was the ball released? The release velocity was 10.64 meters per second at an angle of 58 degrees. So you'll learn how to do this a little bit later on, but for now, let's just say that the vertical velocity is 9.02 meters per second. That means how fast the ball travels upwards. And the horizontal velocity is 5.64 meters per second. That means how fast the ball travels to the right. So let's look at how we are going to solve this problem of how long the ball was in the air before it entered the basket. We'll use a physics concept called the SUVAT equations, and that's just a set of equations that links an object's displacement, initial velocity, final velocity, acceleration, and time. So it's easier if we split the problem into a vertical portion and a horizontal portion. Here, let's look at the vertical portion first. The ball height changes constantly as the ball travels towards the basket. So we'll assign it a variable h, and it's given by the equation here, negative 4.905 t squared plus 9.02 t plus 1.9, where t represents time in seconds. The 4.905 comes from gravitational acceleration. The 9.02 comes from the initial vertical velocity of the ball, and the 1.9 comes from the release height. If you recall, the ball follows a maximum curve, so that's why there's a negative sign in front of 4.905. So given that we have this equation that describes the ball's height at any particular point in time, what we want to do is figure out when does the ball's height equal to the basket's height, because it can only enter the basket when the heights are the same. If it's too high, it'll hit the board. If it's too low, it'll fall to the ground. So we want h to equal to 3.05. That's the basket's height. We plug that into our equation, negative 4.905 t squared plus 9.02 t plus 1.9 equals to 3.05. Then we move 3.05 to the left to get the equation that you see here. Then all that's left to do is to solve it using the methods we learned in Chapter 2. So using the methods we learned in Chapter 2, we can solve the equation using the quadratic formula or by completing the square. I'll assume you already know how to do that, and I'll just include the answer, which is t equals to 0.138 seconds or t equals to 1.701 seconds. That tells us that the ball reaches a height of 3.05 meters at 2 points in time, when t equals to 0.138 or when t equals to 1.701. And if you can see the quadratic curve, it's very clear because it intersects that line twice. The first is at the basket, and the second is actually earlier on. How would we know which is the right answer? Intuitively, it would make sense for the answer to be 1.701, but let's just take one more step to confirm our answer. What is that one more step? We will use the horizontal portion of the SUVAT equations. Recall just now the horizontal velocity of the ball? That gives us an equation for the distance away from Steph Curry that the ball is at a particular point in time. Let's call that d, and it's given by the equation d equals to 5.64 t, where t is also time measured in seconds. Just plugging in our solutions from the previous page, when t equals to 0.138, the distance away from Steph is 0.778 meters. This doesn't match what we want, because what we want is for the ball to travel 9.6 meters to the basket. So this can't be the answer. Then when we plug in t equals to 1.701, the ball would have traveled 9.594 meters away from Steph. And that gets us very close to the answer that we are looking for, which is 9.6 meters to the basket. Therefore, the answer is that the ball was in the air for 1.701 seconds. Of course, this is all an approximation. It's very difficult to know exactly how far he was away from the basket and the exact angle and speed at which he released the ball. But this gives us a pretty good sense of how we can use quadratic functions to solve problems in real life. And in the next page, we can check our answer against what actually happened. If you take a look at these two screenshots, these were taken when Steph released the ball and when the ball went into the basket. And if you pay attention to the timer circle in red, you'll see that on the left hand side, there were 2.6 seconds left in the game when Steph released the ball. And on the right hand side, there were only 0.9 seconds left when the ball entered the basket. That gives us 2.6 minus 0.9 equals to 1.7 seconds that the ball was in the air. That is actually pretty close to what we estimated earlier of 1.701 seconds. In fact, once we learn about quadratic functions in this chapter, we will be able to answer more questions, such as what was the highest point reached by the ball? How high was the ball above the ground when it was 3 meters away from the basket? Or maybe what if there was no basket and the ball fell to the ground? How far away from Steph does the ball land? And how about this? For what duration was the ball higher than 4 meters in height above the ground? I won't work out these answers one by one, but I've included what they are in the brackets, as you can see. We'll go into the details of identifying these properties and how to work these out in the following videos. That's all for today. Remember to stay curious and always follow your dreams. See you in the next video. Thanks for listening.